Hey class, one more example from Unit 2 on the ponder. I thought this was a pretty interesting one. So it gives us a countersunk hole here, and it wants us to find the distance from the top of the hole, from the surface, down to the bottom of the countersunk portion, so where the shaft of the hole begins. It gives us some dimensions. It gives us the diameter of the portion that goes all the way through. So that's 20. That's this portion. That's the diameter or the distance from here to here. And then it also gives us this symbol as the countersunk or the countersink symbol, and the diameter at the top of the hole, which is from here to here, it gives us that as 40. And it says that it's a 90-degree angle. What does that 90-degree angle refer to? If you watch the video, Brother Schellenberg explains this even more, but I'll just kind of put this on here to illustrate it for this video. What that 90-degree angle represents is the angle if you were to extend the countersunk lines on this cross-section view. This view here, section AA, is if you were to cut halfway right down the middle, looking at it from here, and then look at it from the side. So if I took a saw and just cut that across and then turned it and looked at the side, I would see that this would form a 90-degree angle if I extended those lines. So that's what that looks like. Now what it wants again is the distance from the surface down to the end of the countersink where it meets that shaft, and it wants to know how far that is. How far down does the countersink go? And it doesn't give us that, and that might seem a little bit mysterious at first, but if you use a little bit of geometry, then you can figure it out. And there are probably other ways to figure it out, there always are, but this is how I would look at it. So I would look at it and say, okay, well this to me, from here to there and back, looks like a triangle. And I know that it's a 90-degree triangle because it tells me that right here. So, but that's not what I want to know, right? I want to know what distance vertically is from here to that top surface. Well, I'm just going to be curious for a minute. I'm going to play around and see what I can come up with. That's kind of a good strategy, actually, is to be curious. Try and just play around and see what facts you can gather as you're muddling around with it. So I'm going to say, what if I were to cut this triangle in half? What if I made another triangle that went from here down to this point and up to here and over? What does that look like? That looks like, well, I know what this angle is now, because that's just 90 divided by 2, right? From this blue line to this green line, that angle is going to be 45. And I also know that this is a 90-degree angle, so this angle over here, if all triangles have 180 interior degree angles, or degrees from the three angles, this must also be 45. So I've got 45, 45, and 90. So that still doesn't tell me anything about this height right here, but it does get me closer. This is the height that I want. This is that height, right? I know what this is. Well, I want to know what this is. What do I know? I know, again, that I know what this angle is from here to here, and oh, I know that from here to here, across the countersink, is 20. I also know that this, is 40. Sorry, countersink top distance is 40, and I know that this distance is 20. So if I know then that this is 40, I could cut it in half where this line is. I know that's 20. I also know that this is half of 20, so 10. So if the distance from here to here is 10, because that's half of 20 that we're talking about right there, I know that this distance from here and here, from here to here, is also 20. So 20 minus 10 gives me 10 from this blue line to this corner right here. Now, one of the properties of 45, 45, 90 triangles is that the two legs will always be the same distance because those two angles are the same. So if this distance is 10, then this distance must also be 10. There you go.